Ron Garcia. And for our first talk, we'll be having from Texas A&M. And we'll be giving a talk. He's titled, it basically says that using algebraic structures to understand constraint solving makes it easier to recognize properties.
Thank you. Yeah, so the plan was that once you read the title, you don't have to read the paper anymore. There's the title, expressing monoid data for constraint system as a community is one that makes many of the properties of it. Mane Hadarani is here as well, and John Freeman's included Matt Michael's not yet, it's a collaborator. So the paper is really looking at these things called hierarchical multi-way data flow constraint systems that were sort of popular. Constraint systems in UIs, graphical user interfaces. Maybe someone remembers AMOLED, Garnet, or those kinds of systems that try to take control of all the dependencies or express dependencies in user interfaces with constraints, and then have them automatically some values change, other values will change automatically, and propagating these changes throughout user interfaces. So we have a project where we do this kind of thing, and the idea is that we're not really going to say here, maintain all UI state in the constraint system, but we maintain a substantial amount of the UI state in a constraint system, and then express behavior of the user interfaces algorithms we can kind of parameterize over these constraint systems, generic algorithms, parameterize over and then so the idea is that we wouldn't have to write event handling logic, which is usually messy. So most of the behaviors would come from the library. So in this paper, we look at this is kind of a report. When we took a closer look at the constraint systems and try to understand them better, in order to be able to write such algorithms and to describe UI behavior as algorithms over these constraints. And it has brought us some clarity, so we use easier reasoning and some future possibilities of more optimized solvers. I'm going to explain what I mean by that. It's really not a big change of how people used to view these constraint systems before. Kind of a really tweak, but it's small tweak, but it's enough that now we can use graph algorithms directly. We can view them just as graphs instead of some special pieces of data needed in data structure. Things are just graphs, and the information is still in paper, and we can break them out as we want to. So, to situate what we're doing, there's did I lose my title? Is this? Oh, I guess it's sufficient. It's okay. So, like I said, constraint systems are being typically used for the layout kind of. In GUIs, they've ended up being constraints that are being used for layout mostly, but more recently, people are trying to put constraints into this what's called a view model. View model part of a GUI. And what's the view model? There's this pattern, model view model pattern. It's kind of a version of the MVC variation of the model view controller pattern. For the cases where your presentation logic or just the logic and data and dependencies within the UI itself are complex enough to store pretty easily. You can create a model for it. So you could think that the typical MVC, there will be some kind of a UI maybe UI for controlling some data. The model would be the image and the operations of dealing with the image. And your view would be, I don't know, here part of the view would be scaling the data, scaling the size of the image, or controls because of that. Now, instead of thinking that here's a view and here's the model, we would add some kind of an intermediate thing to deal with all the dependencies just in that view. And why do something like that? Well, if you look at the slide title says simple UIs are not that simple. So even if you look at very simple UIs, the dependencies there are actually tend to get very complex. So even this little dialog that you would have some dependencies, you could scale an image by specifying absolute dimensions, or you could specify relative dimensions, and you could preserve the aspect ratio. So there's dependencies, you change some values, other values have to change, but which direction it supports, many directions depending on what you're editing and so on. So if you track the dependency, there's some WX Python code, some kind of that traditional whole framework for doing event handling, and looking at what kind of dependencies are there between event handler and values. You'll get a big mess, and the hope is then that you'll get from a kind of an ad hoc, complex, incidental data structure something well defined that's easy to reason about, and write something generic algorithms over that, and then get rid of complex event handling code becomes a simple data model, a simple kind of declarative specification of dependencies. Okay, so what are these constraint systems? Constraint, everything is a tuple, always so are constraint systems. So you have a set of variables, and then you have a set of constraints. Each constraint deals with a subset of those variables. And every constraint is also a tuple. What are the capital R is a set of variables that constraint is dealing with. Lowercase r is some relation that defines when the constraint is satisfied. If the variables have such values that are satisfied, then everything is good. But it's hard to satisfy a relation. It's not really an algorithm to tell you how you can bring up a valuation that will satisfy the relation. So therefore, constraints in this typical constraint system have a set of methods that are means to come to a valuation that will satisfy the relation. So basically, if you have some n variables, the method will be taking a subset of those n variables as inputs and producing outputs for the rest. And you can have multiple methods in all kinds of directions to come up with values to satisfy R. And these are considered to be black box from the solver's perspective, so the programmer specifies the methods, and it's assumed that it's up to the programmer that the relation will hold once the method is executed. And the whole point is then to bring, so solving a constraint system is to produce a valuation that all of those methods are being, all of those relations are being satisfied, and you have to, the solver's task is to find which methods should be executed and in which order, so that you don't trump previously established relations or invalid. So here's an example of our method scaling, of image scaling constraint system. Let's say 6 variables, 3 for width and 3 for height, so there's initial, absolute, and relative values. We will have 3 relations, one for the width values, one for the height values, and we can compute the absolute, let's say absolute width from the relative width and initial width, and the relative width as well from absolute width and initial width, and then the same for height. And then you would have in the case you want to keep the aspect ratio constant or the same, you would have one relation that for traditionally, these constraint systems, how people view them as graphs are a natural notion of thinking about this. So how people view them is, well, a constraint system. I apologize, this is a slightly different set of constraints than in the previous slide, but anyway, so here we have 3 constraints, number 1, 2, 3, and those E, F, P, A, C, D are variables. So how people view them is each constraint. Well, a constraint system is an under-directed graph, and every constraint is one constraint node connected to a bunch of variables. And then methods are this auxiliary data outside of the graph, but there is this means to direct each of these constraints, each of these undirected kind of subgraphs, and give them a direction, so you have to select one way of directing them. And then solving means that you will select from these possible directions, one of these, I mean, you will direct all of them like these pieces of the graph. And you have to come up with a plan where, then what is it's called a plan is a kind of a valid solution. And when something is a plan, well, it's a plan if there's no cycles, in the graph, and you don't write, there's no images, no 2 or more images, well, at most 1 image to every variable, so you don't write some variables twice. And once you have a plan, then coming up with the valuation is just evaluating, or executing those methods in a topological order. So this kind of a view, well, we can do that, but then it's not really, it's very dedicated and special for this particular purpose. Any reasoning we do, any algorithms we write will be about that particular data structure. If you think of compositionally, so the notion of a constraint and a constraint system is different, and the method and the plan are different. So what we'll see, there's a slight change. We're going to be able to just view them as the constraint, unified constraint, the constraint system, unified method, and then we get a plan. Okay, so this is our view of how we view it as a graph. It's very, like I said, it's not a big jump. And this is kind of a very direct way how we can actually evaluate with these as well. So every method, instead of being a way to direct an undirected graph, it's just part of the graph. So every method is a node and connected to its inputs and outputs. And so then what's a constraint? Well, it's a collection of those methods. And I put a little wavy link between them to show which methods belong to the same constraint, but you don't have to do that. It actually, there's something called a method restriction in these systems, which says that in each constraint, every method will use all of its variables as inputs or outputs. So if every method node that has the same neighborhood, if 2 methods have the same neighborhood, then they will belong to the same constraint. Okay, so all the information is directly in the graph. And so now, what happens is instead of thinking about undirected graphs and then directing them, we have the same graph all the time, and methods become just subgraphs within this graph, or constraints are subgraphs of this larger system graph. And we can actually, when we combine methods or combine constraints, we can think of, we can still think of method as a collection, constraint as a collection of methods. Now, if we compose constraints, we can still think that as the same way. Now we just have more variables, and instead of a method being a graph with just a single method node, now it's a graph with 2 method nodes, and or more nodes. Any graph that is a valid plan. So compose methods and take all the kind of solve that constraint system, take all the possible plans, and retain them as methods. So plan becomes a subgraph. constraints is then again just a constraint defined as a graph of graphing methods. And these are all the operations are just graphing rules, nothing special. So what does the monoid view look like? So how do we make this a monoid? So the representation is constraint is a set of method graphs. So now the method graphs is it doesn't have cycles and it doesn't run twice to one variable. That's a variable. And the set of these constraints is the higher set of the monoid. So what's the composition operator? So if it's constrained in a collection of methods, then we take all possible combinations of combining those methods and throw out the bad ones. Basically, we see which ones end up being non-times and then throw them out. And the operation is just graphing. And then now after this operation, we have another constraint with a bunch of methods. Each method just has more. The properties like associativity and commutativity, they follow because graphing. We're not talking about disjoint graphing, non-disjoint graphing, and those are associative. Identity element is just the singleton set whose element is the null graph. The union with null graph, the graph stays the same. There are some other properties that we have some as well. The empty set is the absorbing element because I think the partition product with the empty set end up getting the empty set. It's also idempotent. We haven't used it for that follows. So just to make it clear with an example, so here is unfortunately yet another example. Some pictures were available to use for slides. One has to always do the use of Generic Programming. So here's two constraints. Think of area and perimeter and height and width. So you can height and width determines area and determines perimeter, and you can also compute the various directions there. So there's two constraints with three methods each in that system. And when you compose them, so that the result of composition is already shown there, but the representation in this monoid line would be this collection of these lines. So these would be no individual methods. All the valid ways that we could solve this system or bring bigger evaluation. Okay, so to make it concrete, so just to give a Haskell implementation for that, some imports. We're using the Martin Arring's functional graph library. The definition of a constraint is just the last line, just a list of methods, and method is just a graph that directly from the library, and we only have to specify. The definition of the graph takes a label of the nodes and label of the edges. We don't need edge labels, but the node labels we can specify whether it's a method node or a variable node, since it's a bipartite graph. Instance of a monoid or empty. The identity element is just the constraint with the singleton list of empty. And null graph and append. We do a method union operator or defined below for all the possible pairs, and then cat maybes that might return nothing, so cat maybes will throw away the nothing values. And okay, so what's going on here? Right. So taking two methods and producing a method, we're just taking the nodes, and there's no graph union operator in this library, so we just tear it apart and take the union of just diagonal defined, so union of the nodes and union of the edges. We create a new graph, and so that's a candidate new method and we keep it if there are no cycles in it, or if all the degree of all the variable nodes is at most 1. And that's just, we don't actually have to check all of it. There's a subset of variables that we need to check. Okay. So what do we gain by that? So now the algorithm for computing all the possible plans or solving the ways to solve the constraint system becomes very simple. So, or basically we just compose the variables. It may be very inefficient, that's not really the point here. If you're just interested in one plan, there's more efficient quick plan, and all of them will get it. Think of composing them in a smart order. So that, here we might end up creating very large data structures. Okay, first let me tell you a little bit more, quickly tell you what kind of system we're really dealing with. That was a kind of static constraint system with a fixed set of constraints. When we have user interfaces, we typically end up with under-constraint systems in the beginning, where there's just some dependencies in the constraint system between your widgets. The UI has multiple ways of propagating data, and somehow we have to determine which way we want to determine it. So there's many ways of selecting methods to bring consistency in the UI. So what we do is we add more constraints to make the system over constraints, and then give some strength to each of these constraints and prioritize the constraints so that we can throw away the weaker constraints that are less important than that. Where do we get these strengths and weaknesses, or the strengths from the update history? So we're trying to values that you preserve, that you just edited, you want to define. We want to make constraints associated so those strong so that they will be preserved. So taking a constraint system, every variable gets what's called a state constraint. And so the state constraint is one that will, if it is enforced, it keeps the value of the variable. So we will then, the variable we want to preserve, we will apply state constraint. And then the evaluation will be one that manages to the primary one that manages to preserve some state constraints, but others will have to control. So this more complicated algorithm is a little bit more complicated, but basically how you get to this is you start with the under constraint system, add the state constraints, and then you try to go in order and throw away the ones that do not succeed. That gives you the locally best predicate, better solution and the best proposals defined in the constraint system. So, right, and you just follow this operation that tries to compose and keeps the result if it succeeds. So other things we gain is easier reasoning. So if we might want to answer questions like, can the user interface ever override the value of any field that the user is editing? So you might want to answer this kind of question when you're a UI designer. Seeing that from an event handling logic may be really hard. Now it's really just piece of Haskell that you can answer it this way. You take the original constraint, you add each constraint at a time, each state constraint at a time to define it or the system, compose the system with one additional state constraint, and is there always going to be a solution? If you end up with an observer, then you know that you will end up overriding your value. Or if you edit fields in this order, will the interface modify this or that, and so just thought that basically we know we get results of say, it's easy to see properties of each. The strength of the enforced constraint does not change the best plan, so this helps in knowing when do we need to rerun the solver, the planner, when there's some interaction from the user. It's just simple dealing with these monoid properties. We're really working on this. This was an aspect of the show, but we're really working on the JavaScript library for the UI building. And so what happens is when we serve a page with using this technology, well, we pass several will contain the solver and will contain the constraint system, and then it starts to run an evaluator over there. It usually is the case that once you pass the model or the constraint system to the client, it doesn't really change anymore. And you might, in some cases, it might be much more efficient to instead pass the solver, but just to specialize the solver for that particular case, and maybe it turns into a bunch of if statements. Or maybe you could take part of the constraint system and compose a lot of the constraints that, especially if they don't expose the number of methods. There's also dependencies and the number of methods remain low. So these kind of things would be easy to directly just run this, analyze this by computing with this number, computing this convolutions. Okay. So that's it. So as a result of this kind of activities that we've done, we have a better understanding of the data flow constraint systems. We got some readers, some easy planner algorithms, easy tool building. We may have a visualizer for these dependencies on UIs, which is very easy to build next to this view. Some of the reasoning activities become really clear, and we haven't engaged into that last thing I mentioned, but it gives us a starting point for this. Okay. Thank you.
So our discussion for this talk is going to be Neil Krishna-Swamy. So I'll pass the floor on to that.
Okay. I don't have the mic, so if I'm not speaking loudly enough, please let me know. So I thought this was very interesting work, sort of from two ends, one practical and one theoretical. So on the theoretical side, there's been a lot of work on constraint solving program, CSPs in sort of algorithms and complexity model. And I had never really understood that at all. And so I wanted to basically thank you for writing this paper, because now I understand what all these graphs actually mean. But one question that came up reading them is that there has been a lot of work in the algorithm community on this, and there seems to be quite a lot of theoretical work on constraint solving problems and like optimality for it and things like this. And the algorithm you specified is very simple, but it seems like a lot of the algorithmic work that's gone into these things is sort of missing in the sort of duofold over the constraints.
Yes, yeah, definitely so. So I mean, the kind of classic way of if you're interested in just one plan, often finding the best plan. Algorithm to do that is called quick plan, and it proceeds with this degrees of freedom ways. You find first a constraint that if you fix a method in that constraint, you don't limit your search space. I mean, you don't limit your choices in the remaining ones. And if you do clever ways of maintaining what they call a list of free variables, which means something different than free variables mean to us. But anyway, and you can do that basically in a linear fashion. And then when you have this hierarchical solver, then it's with some constraints you can do another linear pass. So it's n squared, assuming that your constraints don't span all the variables.
Yeah, so that led me to the question of like, did this monoid view like help you at all with the correctness groups of these more sophisticated algorithms, like organizing the groups? Like also like the way you specified this monoid, it seemed like an alternate thing you could have done was specified it as a partial completed monoid, because you say I'm forming a monoid by taking two sets of constraints and then taking the Cartesian product and seeing if each pair is compatible. And so you could alternately view it as saying I'm defining a partial monoid where you take two individual constraints that might or might not lead to
right. Yeah, so the first part of the question, I guess, was whether it helps understanding these other algorithms more. We haven't done anything concrete, but now suddenly they seem much clearer now. But of course, we'll be staring at them. The other part is, yes, you may not want to, and you might kind of, with this monoid view, just as a composition, you might get to this one thought lingering in my mind has been, can we get to the performance or the complexity of these faster algorithms by selectively, sometimes not evaluating, but keeping them as a really deep part. Okay, well, this section we don't want to bother at this point because it expands too many things. And so, yes, definitely you could just view it as you just compose finally, and then you don't know quite yet whether the result is
yeah, and so that exhausts my theoretical questions about this. So practically, it's been, I actually have looked at Garnet, and like this probably dates me. But one thing I was never very clear on with those kinds of constraint-based graphical user interfaces is that the constraints seem extremely good for handling sort of view state. Like you had the example of you want to resize an image, or you may want to modify some parameters in response to the user input, like if you want to maintain the aspect ratio. But when you actually perform a change on the image, say, like that might be a disruptive operation.
right.
And the question I had is there any, so naively you would have to just throw out everything once you actually make a change to the model and start over. And I was wondering if there's any way to sort of save work when you like you have this split between the constraints that are managing some view states and then some underlying model state which gets changed in sort of distracted increments. And so is there any way to save your constraint solving if you make changes to the underlying model?
One could analyze what, so the way we view things are, well, if you look at the dialog or something like this image scaling dialog, you model that as a constraint system, and then there's some commands that are tied to that dialog, and you collect data to commands are output variables in the constraint system, and then when it's time to actually do the scaling, it's you're invoking some operation in the model, and the task of what the constraint system is doing is kind of doing the synthesis of parameters for that command, and then that particular action doesn't itself, there's no feedback to the model, to the view model anymore. It could if the image changes, then your initial values, but it would have to be then encoded as you launch a new constraint system. But yeah, what's interesting is when you say one could then analyze it, okay, you want to preserve everything else, but what if you just bring in these two values?
Yeah, and I mean another aspect of that is like this is good for handling the ordering constraints on the it handles them by like letting you not think about it, the ordering constraints on the view model, but when you perform commands on your underlying data, there's some ordering constraints you have to respect there as well.
Right.
Do those encode well in the frequency?
you might have sort of these external events happening. They have to happen in a certain order,
Yeah.
and then the model would have to enforce such things. You can't say directly whether you have to express it in some kind of a valuation changes in the model, and then so one of the things that we do automatically, what I mentioned is we're looking at algorithms encoded, the UID waivers encoded with algorithms parameterized by this model. One of the things we're doing is enablement and disablement. We try to get rid of that explicit code, and we do that by tracking which values contribute to or do not contribute to some of these commands. And so it might be that through those kinds of mechanisms, that's an interesting question.
Yeah, any questions?
Yeah, just ask about the package, okay? So I think your Haskell implementation looks very concise, it's very beautiful, and very helpful for optimization feature.
Yeah.
And so, but now there are actually not such kind of constraint solver, I think. I remember sometimes Sky Blue or some kind of things actually are used to solve these kind of things.
Yeah.
So the main problem there is how to do incrementalization, like you said. Incrementalizations on the data is views, the data, that is you edit something. And on the other hand side, incrementalization on the constraints change. Some constraint I lower its priority, for example, I raise the priority, or I revoke the constraints.
Right.
And all the things need to be recomputed. But what is difficult is how to propagate these kind of updates. Okay. So I'm not so sure in your current implementation or your framework, very beautiful things. Have you thought about that, or can you combine that kind of thing to this kind of monoid?
The early part of
Yeah, I think
2 minutes ago we kind of discussed that was
right.
was roughly about it. And we will probably look at that at some point if it can be combined. But yes, definitely. So there's the incremental. If you have a solution already, if you add a new constraint, or if you change the priority, that you can model it as removing a constraint and adding a new constraint. These operations where removing a constraint is easy, but adding a constraint, it's all the algorithms. The worst case complexity is still the same as solving it from the beginning.
Yeah, you solve it at the beginning,
Yeah,
then
right.
you solve it out. That's good.
Right.
Okay, but actually in practice, maybe that is you have the constraints really maybe too many. Okay.
Right.
Yeah, I remember it seems in software engineering is kind of maybe
Right.
constraints or meanings.
Yeah. So this Haskell code wasn't really intended to do it. Okay,
Right.
plug that into your compiler. So in the practical system, so in what's called the hot drink is that
Right.
because they're all implied. The name comes from all the systems are called espresso and cappuccino. And ours is more generic. So it's fun. So where it's kind of a derivative of QuickLand and the algorithm running there. Good job.
Just to say a quick note, so have you ever taken a look into XAML? XAML, XAML?
Example? Okay. Yes.
So the idea, as far as I can understand it, was that you decouple the job of specifying your UI from the programming parts of the system in a way that is language independent.
Right.
And then things like these are somehow bits that no side really wants to take the responsibility of. And I guess that what that particularly means in this discussion is that you have to have a good when you approach Microsoft and tell them that, well, you know what, we can handle that. So,
Eventually, hopefully, yeah. So lots of, I mean, in a sense following similar in the Kotlin thing, you'll specify your view in HTML, and then there's a view model specification, which looks kind of like a little piece of code that actually was too small to see, but it's kind of it's a JavaScript EDSL embedding in a specific language that specifies this constraint. And then there's yet another specification which is bindings between the bind to the model and there's lots of declarative UI things are doing. UI frameworks are doing that kind of.
So it seems like this could be generalized from GUIs to just some sort of reactive program like robotics. Is there something I'm not seeing that prevent that? Is it specific to GUIs?
No, yeah, you're right. It should be, and I'm going to be very happy to find more applications. We've looked into, so the other part that I only discussed in the beginning was trying to identify generic algorithms or reusable behaviors in GUI systems, and that's sort of one part of our interest and so on. Enablement, disablement, value propagation, or visualization, automatic visualization, or undo read, those kind of behaviors. And then those tend to be GUI specific, specific to those, but I'm sure in other domains there would be similar things that could be important.
One question, and I guess it should be the last one. So, when you're talking about, you had an example which has the area and the height and the perimeter, and my impression is that in that particular case, everything's sort of bidirectional, that you put one in, you can invert the computation. Can a system like this accommodate things that are not bidirectional? So if I choose one thing here, then it can flow, but perhaps going the other direction is not fully well defined, and so I want to be able to force the user, for instance, to say, well, if you update this, then you have to update some other thing in order to get everything, in order for the rest of the system to become consistent automatically.
It doesn't have to be bidirectional. Information can flow to any direction. So if you have two variables, you can define two different kinds of, actually four different kinds of methods. One that flows outwards and has two inputs, and that has no inputs, and then one that goes both ways. And one three, you can go 2 to 1 to all directions, 1 to 2 to all directions. And so, but whether you kind of stop and ask.
I guess invertible maybe that was.
Yeah, things go to all directions, and you can model. We find that we have a heuristic of you try to preserve each and every the most recent values. First, sometimes there are situations where you want to affect that. One of the features would implementing kind of reusable behavior is pinning. You want to pin some value in the user interface. The nice thing about this system is that you can just, that is a feature that you say, I want pinning, and then every variable has it. Every one of your widgets will have a pinning feature, and you can just click that and make sure that that information always flows outside of that. And if it's not possible, there are no such solutions, so if you can't pin it, things get disabled. So yeah, I think